a big flow of information. So with regard to, we know what happens in here. All of these arrows I've drawn are all electrical signals, right? I mean, they're all electrical signals. And electrical signals, we know to have current, right? The flow of an electrical signal, you need to have a potential difference, charges across a cell membrane, that is greater than whatever the resistance is to flow. And you'll notice here that we have some things in here to help us lower resistance, right? Those insulating Schwann cells, the purpose is to help lower the resistance. Question?
Are we going to have to know, like,
Don't ask me, are we going to have to know? Oh, you mean like the abbreviations?
Yeah.
If it's helpful for you, what is this?
I,
I mean, that's Ohm's law. No, I'd rather you know what I means, current, the flow of electricity. Okay. So we're good with that? So that's kind of what happens. So let's look at this now here. Let's use the language of electrical signals. And the language of electrical signals is going to be determined by this voltage difference, right? The potentials. When we talked about how cells at rest have a resting potential, what was the strength of that resting potential? 70 millivolts. What's the direction? What's the inside relative to the outside? Negative. So that minus 70 millivolts is largely determined really by the concentration of the ions we talked about and their relative permeabilities across the cell membrane. There's a section in your textbook, I don't want you to worry about it because it's really beyond the scope of what we need to do, but you can estimate, if you know the relative concentration of ions, sodium, potassium, chloride ions especially, you can calculate for any given concentration of those ions and their distribution across the membrane, what the value of the resting potential is. It's called the Nernst equation. Like I said, it's beyond what we need to do. I mean, we could do it, but so what? I mean, you're never going to have to, in your careers, calculate resting potentials, but you do need to understand what these potentials mean and do. So we won't worry about that. I'll tell you this, though, that for the most part, the most important ion in determining potential differences is potassium. But we'll see the ion that always starts, well, not always, but almost always starts the flow of electricity or current is a movement of sodium. So we're going to spend a lot of time here in a few minutes talking about the flux of sodium and potassium. Flux just means movement, right? The movement. And I like to use the word flux because flux means change, right? If something's in flux, it's moving or it's in change. And we can simply say influx and efflux because we are always talking about the movement of ions relative to the cell. Influx would be a movement of whatever ion we're talking about into the cell, right? Efflux would be a movement of ion out of the cell. So I like those words because they're simple. If I say sodium influx, that doesn't leave anything other than the fact that you know what's happening. Sodium's moving in the cell. If I say potassium efflux, what does that tell you? Potassium's leaving the cell, right? So try to get comfortable with those words. It really helps us. We don't have to say, oh, sodium moves into the cell because it's moving with a... I mean, we don't worry about it. Just influx and efflux. So this is the resting potential. Now we mentioned that this potential can get more negative or less negative, right? And if it gets more negative, we call that hyperpolarizing. And if it gets less negative, we call that depolarizing. Does that make sense? So those movements away are something that's important. Now let me give you some values here. An action potential is a depolarizing potential. And I'm going to give you what it is right now. It is plus 30 millivolts. Just to kind of give you what that, just give you a number. And now let's figure out what that means. So that means that the strength of the potential difference across the membrane is 30 millivolts. But now the inside is positive relative to the outside. So from minus 70 to plus 30, is that depolarizing or hyperpolarizing? Depolarizing, right? Hyper means more negative. That's definitely not more negative. In fact, that's gotten the opposite. That's gotten what? More positive on the inside. So even though it's still polar, it's depolarizing because we've gone from minus 70 to minus 60 to minus 50 to minus 40, minus 30, minus 20, minus 10, 0, plus 10, plus 20, plus 30. So we are moving in that depolarizing direction. Now, should every stimulus trigger a response? No. Because your brain honestly couldn't handle all of the information coming at a particular time. Right? So just like anything, what should your central nervous system worry about? It should always triage, right? It should always take care of the most important things first, and then the least important things last. Right? And the most important things are always going to be the ones that have the strongest stimulus, right? Because that means they're going to be the furthest away from homeostasis. The lower the stimulus, the closer they're going to be to homeostasis. You with me on that one? Okay. So a neuron, we have to apply that to the level of the neuron as well. Should every single response trigger an action potential and send a signal and cause the release of a neurotransmitter? Absolutely not. So we need to have integration here, right, to decide, is this stimulus coming in here strong enough to make me want to release a neurotransmitter down here? Okay. Now, that involves the understanding of there's something called a threshold. You know what a threshold is, right? This is a threshold. It's something you pass across. Right? So that's a threshold of the door. You pass across it. So a threshold value just means it's a value that we reach and exceed. Right? We pass across.